Welcome back to this video course on pulse width modulation for power electronic converters. So, we have been covering several different modules. Like the very first module we covered was an overview of power electronic converters and various DC-DC converters and voltage source and current source converters and multi-level converters and so on. And then we specifically looked at the applications of voltage source converter. Then we looked at the purpose of pulse width modulation, and then we looked at particularly PWM at low switching frequencies. And from this point onwards, we have moved to fairly high switching frequencies. We have been considering switching frequencies which are much higher than the fundamental frequency. So, this is the first this is a very commonly used approach, triangle comparison based PWM. That is, we use a set of 3-phase modulating signals and compare it against a common triangular carrier to produce PWM signals, and this is what is triangle comparison based PWM. So, we discussed this in one of the modules, and subsequently we discussed an alternative way of PWM generation, which is the space vector based PWM. So, we produce PWM on this using this notion of space vector, and we also looked at how these two are the same and also these two are different, that is what is common and what is different between these two. So, we observed that whatever PWM waveform can be produced by the triangle comparison can also be produced by the space vector PWM, but certain PWM methods, certain PWM waveforms generated by space vector cannot be done using triangle comparison. That is, we said that space vector based PWM is more general than triangle comparison based PWM, and the specific example is advanced bus clamping PWM that we have here. So, which is possible through the space vector approach and not possible by comparing this triangle the other way of doing it. So, after this we are now getting started. So, these modules, the two modules focused on how do you generate the PWM signals, and now we are beginning to understand do some analysis on how how much is the distortion that is caused and so on. So, this is about PWM generation. Here we are getting into analysis. The first kind of analysis that we will be doing is we will be looking at the line current ripple. That is, the output waveform what you are producing is not perfectly sinusoidal. There are sinusoids and also there are harmonics added to that, and because of the harmonic components in the voltage, there are going to be harmonic components in the current, and therefore, there is going to be a ripple in the current over and above the sinusoidal current. The line current is not going to be purely sinusoidal, on top of it there is going to be certain amount of ripple. So, analysis of this line current ripple is what is the new module which we are going to be discussing over the next 4 lectures, including the present one. So, we look at this analysis of line current ripple. What is it that we would do in this is, we would do a review of various PWM techniques which we have covered in the last about 8 lectures or so on. We would take as we progress, we will review them also, and we would look at the maximum fundamental voltage that is possible with a given DC bus voltage. Let us say you have a fixed DC bus voltage of 600 volts or so. How much is the maximum line voltage that you can produce? It slightly changes from one PWM method to another PWM method. So, as we that is something like on what we can call as DC bus utilization. So, we would look at that is one of them, and we would look at the harmonic spectra. The fundamental component is one of the frequency components. If you look at the PWM waveforms, it would have the fundamental and it will also have a lot of harmonics. We will try to get some understanding of the harmonic spectra. So, for example, at what frequencies would you expect the harmonic components to be, and so on. And once you have harmonic spectra, there are harmonic voltages. We need to understand the effect of these harmonic voltages. What is their effect? What is their influence on, let us say, a motor that is being driven? So, that is why we would have a review on the harmonic model also, and we would look at the total harmonic distortion factor, so on and so forth now. So, this part of the work primarily, that is today's lecture, what is given in bold is more from the frequency domain point of view. We would try to understand what are the various frequency components in the PWM waveforms and what would be their influence and so on and so forth now. In the subsequent lectures in this module, from next lecture onwards, we will start looking at it from a different point of view, that is error voltage vector. That is, we will start looking at it from a space vector point of view. The PWM waveform is a 3-phase PWM waveform. There are 3-phase voltages basically getting applied on the motor. The 3-phase voltage can be seen as a voltage vector, and you have the desired voltage vector to be applied, and you have the actual voltage vector that is being applied, and there is a difference between the desired voltage vector and the actual voltage vector, and that is what is called as the error voltage vector. So, we would look at the error voltage vector now. In a different way, if you look at it, you have harmonic voltages. right. You have fundamental voltage and you have harmonic voltages. You have harmonic voltages in all the 3 phases now. So, you can call them as voltage ripple, the sum of all harmonic components you can call them as voltage ripple. Now, transform the voltage ripple in the 3 phases into a 2 phase quantity into the space vector domain, and that is error voltage vector. So, error voltage vector is the space vector representation of the voltage ripple. I mean by voltage ripple I mean the actual voltage minus the sinusoidal the desired sinusoidal component. So, you can look at it as error voltage vector, and what you can do is you can integrate that error voltage vector. Why do we mean by integrating? This harmonic model. The harmonic model of an induction motor is basically its leakage inductance. We have seen this in one of the lectures before, and we will take a quick look at it again today. So, now if you apply voltage across an inductor, the current is going to be proportional to the integral of the voltage, and therefore, we will integrate this error voltage vector, and that gives a quantity called stator flux ripple vector. Because it is voltage, you integrate that, it is going to give a quantity whose dimension same as flux, and these voltages are actually applied on the stator of the induction motor, and therefore, if you integrate them, that gives the kind of the stator flux ripple. So, we call this as stator flux ripple vector, and this is equivalent to the current ripple or its current ripple vector. So, if you scale this appropriately, you get current ripple vector now, and the current ripple vector is nothing but the 3 phase current ripple transformed into the space vector domain. And what do you mean by current ripple? It is a non-sinusoidal part in the current waveform. The current waveform has a sinusoidal component of the desired frequency, plus it has harmonic components. The sum of all harmonic currents we call it as current ripple, and the current ripple in the 3 phases can be transformed into a vector, and that is what we call as current ripple vector, right. And based on this analysis, what we will do is we will try going into the study of RMS line current ripple over a subcycle. We will try to find out how to get this RMS line current ripple over a subcycle, which is a small unit of time, and we would try and study the influence of switching sequences on these RMS current ripple. So, how instead of one switching sequence, we let us say in the conventional space vector PWM, we start with one particular sequence. We start from the 0 state and go to one active state, another active state, and come back to the we go to the other 0 state. So, like 0, 1, 2, 7. Instead of that, you can use a different switching sequence as in bus clamping PWM, where you use only one 0 state, or you can use a switching sequence as an advanced bus clamping PWM, where one phase is clamped, second phase switches once, while the third phase switches twice. So, there are different switching sequences which we discussed in the last couple of lectures, and we would look at the influence of these switching sequences on the RMS current ripple now, right. So, then this RMS line current ripple over a subcycle, you can use that and you can kind of integrate the mean square ripple to get the RMS current ripple over a sector or line cycle. This is what we will do, and this is and we will use all this idea. This is about the analysis, and the last part is about designing. Once we understand how the sequences influence the RMS current ripple, it is possible for us to design a hybrid PWM method, that is a combination of different switching sequences, and which will lead to a reduction in current ripple. So, we will look at this as on the last lecture in this particular module. So, this is what we are planning to look at in this particular module. So, today primarily our emphasis will be here, that is we will be looking at more from the frequency domain point of view. We will try and understand the harmonic spectrum here, and the effect of the harmonic voltages, and so on and so forth. So, specifically I would call this as harmonic analysis of PWM techniques. That would be the lecture today. And what we have been talking of is a 2-level voltage source inverter. So, it is a DC and it produces AC. It is an inverter, it produces 3 phase AC, it is a 3 phase inverter, and it is a 2-level voltage source inverter. So, if you take the R, this is the pole, this leg is a single pole double throw switch, the top is on or the bottom is on. So, it is a single pole double throw switch. The pole is connected to either the positive voltage or to the negative voltage, and there are 2 levels, and therefore, this is a 2-level voltage source inverter. And the kind of load that is connected between R, Y and B here, R, Y and B is as shown here. So, this is a typical kind of load that we have. You can probably regard this as a stator winding of a machine. So, R is connected to the midpoint of R phase leg, Y mid phase leg, and B is to that midpoint of that leg, and N is the load neutral. This is not particularly connected anywhere else, but through the R, Y and B. So, we are talking of load neutral is not connected, we are talking of basically a 3-wire connection. It is a 3-phase 3-wire connection, right. So, a quick list of the PWM techniques that we have looked at in the last couple of modules. So, sine triangle PWM is the most popular PWM method. You use 3-phase sine waves, you compare them against a common triangular carrier, and you produce the PWM signals, right. So, to the sine waves you add third harmonic component. and compare them with the common triangular carrier, and so this is third harmonic injection, because third harmonic component has been added to the 3 phase sine waves now. This is the other kind of PWM method we looked at now. And if you go in for a slightly different kind of common mode injection, you would reach the conventional space vector PWM, and this can also be produced from the space vector domain, whichever way you like it, right. So, this is conventional space vector PWM, and we found that then we looked at 60 degree clamp and 30 degree clamp PWM. These are bus clamping PWM or discontinuous PWM methods. So, in 60 degree clamp PWM, you have a phase clamped during the middle 60 degrees in every half cycle, and in 30 degree clamp PWM, you have a phase clamped during middle 30 degree durations in every quarter cycle. And continual clamp PWM is a generalization of 60 degree clamp PWM. The phase is continuously clamped for 60 degrees, but not exactly at the middle of the half cycle. That is, if half cycle is from 0 to 180 degree, in 60 degree clamp, the clamping period is between 60 to 180 degree, whereas in continual clamp, it can be anywhere between 30 to 90 or 90 to 150 degrees. So, that is continual clamp PWM. And you also have split clamp PWM, that is a generalization of 30 degree clamp PWM. In 30 degree clamp PWM, a phase is clamped for 30 degrees in each quarter cycle, in the first quarter and the second quarter in every half cycle. In split clamp, a phase can be clamped for a duration gamma in one quarter cycle and 60 minus gamma in the other quarter cycle. So, gamma is equal to 30 is a particular case that will take you to 30 degree clamp PWM. And all these methods, the first two are normally generated based on the triangle comparison approach, but if you want, you can also produce these waveforms from the space vector approach, right. That is also possible to do that there. And then you can look at this conventional space vector PWM. This can be produced from the space vector point of view. It can also be easily produced by adding certain common mode component, as we discussed in one of the previous lectures now. Again, all the 60 degree, 30 degree clamp and their generalizations called continual clamp and split clamp, all these PWM methods can be, all these PWM waveforms can be produced either using the triangle comparison approach or the space vector approach. The last two that we are talking of here can only be produced using the space vector approach. So, these use some of the flexibilities that are offered by the space vector approach, namely that of dividing an active vector time. What all these PWM methods do is to divide the null vector time. They divide the null vector time, that is Tz, between the two 0 states, which is minus 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 and plus plus plus. And what this does is, it uses this division of null vector time. It is like bus clamping PWM, uses only one 0 state to do that, it uses different and on top of it, it uses this division of active vector time. These methods, they apply an active vector more than once in a subcycle. So, they are we call them as advanced bus clamping PWM method, specifically as advanced continual clamp and advanced split clamp PWM. So, we would look at the how the frequency spectra would look like in many of these cases, get some idea of the frequency spectra in today's lectures now. So, this is now you have your 3 phase sine R, Y and B, which are like 1 and minus 1 stand for the positive peak and the negative peak of the triangular carrier. And so, you compare this with a triangular carrier, high frequency triangular carrier, and you produce the PWM waveforms which are used to switch the inverter, fine. So, how would the harmonic spectrum look like? That is the question now. So, if you go back, what are the various frequency components here? One is the fundamental frequency, this is what you can call as F1, and the other one that I have not shown here is the high frequency carrier, which can be at a frequency what we can call as Fc. So, now let us see how this should be look like. So, I want to look at the harmonic spectrum. This is frequency on the horizontal axis and amplitude on the vertical axis. So, what you will certainly have is, you will have a fundamental component, let me call this as F1. This F1 is same as the modulation frequency. So, if you were using the low switching frequency PWM, which we were discussing earlier, this is F1. Now, you will also have, this is a 50 hertz, you will also have 250 hertz, 350 hertz components, 5th, 7th harmonic, you will have 11th and 13th harmonic. Here you will not have all that, because your carrier frequency is quite high. So, I will draw a break here, this is a break. And now, let us say you have a switching frequency, you have this carrier frequency which we call as Fc, and then let us say you have this twice the carrier frequency to Fc. Now, what you will have is you will have some harmonic components here. You will have some harmonic components around the carrier frequency Fc, and again you will have some other harmonic components around the carrier frequency 2Fc, something like this. And it can actually go on. Let me extend the line a little further. So, now there is also around 3Fc, there is also around 4Fc and 5Fc. You will have components around this, harmonic components around these things. So, the components around 3Fc, 4Fc etc., as the higher and higher frequencies go, you mean the amplitudes themselves might reduce. Normally, I would say that these two components around Fc and 2Fc are quite dominant. So, what you have is you have a fundamental component and you have several components which are called switching frequency components, and there is a big separation in the frequency between these two. Separation. This can be 50 hertz and this can be 5000 hertz. So, you see there is a 1:100 difference now. So, the many a times what happens is the machine model, the load model itself is different for this and that. So, many a times the reactance offered by the machine itself is substantially high for these kinds of frequencies. Just the leakage reactance itself is fairly high, and these components get very nicely attenuated. That is, though the considerable harmonic voltages of considerable amplitude are applied, the corresponding harmonic currents would be quite low. So, that is the point that I am trying to tell you here now, right. So, there is a very good separation between the fundamental component and the carrier component, because you are using very high frequency carrier signals now. This is only to get a feel for how the PWM spectrum would look like now. So, to just get more into the specifics, I would suggest that what are this. So, there is what you have here is you have the fundamental component at frequency F1, which is the modulation frequency. Then you have the switching frequency harmonic components now, and the switching frequency components you look at here, there is around Fc, you can call them as first sideband, and there are components around 2Fc, you can call them as second sideband, third sideband, fourth sideband, fifth sideband and all that. So, I would normally say that the first two sidebands should suffice, because the third, fourth, fifth sidebands might be, their amplitudes might be lower than those of the first and second sidebands. And further, there is also reactance, there is a filtering effect, since the machine is seen as a leakage inductance. The leakage reactance seen by this and the leakage reactance seen by this are very high. The leakage reactance seen by the fifth harmonic sideband are 5 times the leakage reactance seen by the first sideband harmonics. So, from that point of view also the higher sidebands are negligible. You would normally have to consider only about 2 sidebands here, and the actual frequencies are something like this here. This is the result of the modulation process. The switching frequency components, you will see the first sideband, and the first sideband is around Fc, Fc plus or minus 2F1, Fc plus or minus 4F1 etc. The second sideband you will get it as 2Fc plus or minus F1, 2Fc plus or minus 3F1 and so on. And the third sideband you will find them around 3Fc, 3Fc plus or minus 2F1, 3Fc plus or minus 4F1 and so on, and that we would call as the third sideband, and 4Fc plus or minus F1, 4Fc plus or minus 3F1 etc. that would call the fourth sideband. As I mentioned before, that the first two sidebands should actually be enough for us to kind of have a reasonable estimate of that, but for a better estimate, well, you can always go to consider more number of sidebands here now. So, I would give you this reference for further information on these things, that you could refer to Professor Mohan's book Power Electronics, Converters, Applications and Design, that gives a discussion on these harmonic components with the sinusoidal PWM. And I have not been discussing the amplitudes of these components now. So, what are these amplitudes going to be? That is an important question, and you can find that in this book by Professor Holmes and Lippo. on pulse width modulation for power electronic converters, which I have mentioned in a number of times before in this lecture. And these components are actually the amplitudes are determined using what is called as double Fourier series, and that is out of scope of this course. We will not be discussing this. What would be these exact amplitudes? It is possible to calculate using double Fourier series. You can look at this Holmes and Lippo book or several other published papers in the literature which talk to you about that. And we will not be doing that for one reason, that is we would try and keep our we will not get into details, that is one reason. And what is important is, see, every frequency component, for example, this particular frequency component is going to drive a current, a harmonic current of the same frequency, and this particular component is going to current of a particular frequency now. So, all these harmonic currents can be added up and they get you an RMS current, there is an RMS ripple current. What we are interested in many situations is to find out what is your RMS current ripple. So, we would take the route of space vector approach and we do some analysis based on the space vector approach and try to come up with what is the RMS current ripple. Hence, we will not go into what exactly are the amplitudes of these various components, and normally we would probably look at what is the dominant component in the first sideband and what is probably the dominant component in the second sideband. And so, the details, as I told you, you can look at these two books, and particularly book by Holmes and Lippo for many details regarding double Fourier series and analysis of the spectral waveforms and sine triangle PWM and quite a few other related PWM methods. Now, we would just focus on the important features in the voltage harmonic spectrum. So, what are the important features there? One thing that you certainly can't miss is fundamental component. This is the purpose of pulse width modulation now. This is the purpose of pulse width modulation. What you cannot avoid are the harmonics. There are several harmonics and there are at various frequencies, there are various amplitudes. So, there are number of side bands. As I said, we will consider the first and second side band, and there also we will look at the dominant component of the first side band, that tells you how bad the first side band is, and you can look at the dominant component in the second side band, that tells you how bad the second side band is. And in many PWM methods, interestingly, it would be either the first side band or second side band that will be dominant at different ranges of modulation index. In conventional space vector PWM, for example, the second side band will be dominant in low modulation indices, and at high modulation indices it will be the first side band that becomes dominant now, and that is the reverse in case of advanced bus clamping PWM, as I will mention a little later in this now. So, what we would say is the important features, when you look at the important features, well, one can argue about this as to what is important, what is not important. We are just trying to get a grasp over that. There are non-idealities, all the harmonics are non-idealities in the waveform. We want to understand how significant or how big it is, so on. So, you can probably look at the first two side bands and the dominant components, the two side bands, to get a measure of how bad the waveform could be, or what its quality or so on. And the other component, if you, this is a very quantitative component which gives you a more detailed picture of the harmonic distortion, is the weighted total harmonic distortion factor of the voltage waveform. What we are having is a voltage waveform. So, what you have is, and it has an harmonic component which we can call as Vn, is the nth harmonic. So, that Vn by n, that and whole squared for all n, that is that exists in that, except for n equals 1, all the harmonics like 5th, 7th, 11th, 13th, and all of them are added up. There should be a sigma sign here. I mean, please excuse me, and please include a sigma sign here. So, you should have a sigma of this. So, Vn by n squared would simply mean the nth harmonic alone. This is sigma of all of that divided by V1. This is what is called. So, this Vn by n the whole square is a measure of a particular harmonic. Sigma of Vn by n the whole square is a measure of all the harmonics, and that is normalized with respect to the fundamental voltage to give you the weighted THD of the voltage waveform. We will again discuss this a little later as to why we are looking at this like this now. So, why what is this Vn is the nth harmonic, and Vn is being divided by n. Why is it so? That is because of the motor model, which is what we are going to look at now. So, let us say this is something we looked at in one of the previous lectures also, but I am just doing a quick recap of that. So, you want a harmonic model of an induction motor. Now, let us say the fundamental voltage is applied and there are different harmonic voltages are also being applied. Let us consider a particular harmonic voltage being applied now. So, this is the model for like when for an induction motor at steady state balanced and when a sinusoidal voltage is fed now. So, now the sinusoidal frequency is very high, we are considering harmonic component now, and what you have is this slip RR by S, this is actually RR by S. When you consider a harmonic, the harmonic frequency is much higher than the rotor speed. Therefore, the slip of the rotor is very close to 1, as I mentioned in a previous lecture, and therefore, this RR by S is simply equal to almost R. This S is usually a small number for the fundamental component, and therefore, RR by S will be very big. On the other hand, here RR by S is very small now. So, what you have is a small rotor resistance in series with the leakage inductance, and that comes in parallel with the magnetizing inductance. The the resistance on the inductance in the rotor circuit is much lower than that of the magnetizing inductance. And the first, the rotor resistance is low, and therefore, you can neglect that, and that too at high frequencies. The reactance, the harmonic frequencies are high frequencies, the reactance is much bigger than the rotor resistance. So, you can neglect that, and once you do that, what happens is, this is the kind of circuit that you are going to get. You can use the same argument for the stator resistance also. The stator leakage is much greater than that, and therefore, you can ignore that. Now, what you have is, you have this leakage inductance of the rotor coming in parallel with the magnetizing inductance. This is large and this is small, and therefore, the effective combination can be written like this. It is Ls and Lr. This is the harmonic model of that now. So, whenever you apply certain harmonic voltage Vn, that harmonic voltage Vn sees this harmonic voltage sees the motor as its leakage inductance. So, this Vn drives certain current In, and this In is given by Vn divided by N times omega Ls plus Lr. Ls plus Lr is the leakage inductance, omega S is the fundamental angular frequency. So, if it is 50 hertz, it is 2 into pi into 50, 100 pi radians per second, and N is the harmonic order, that is maybe it is the 101st harmonic or whatever, 113th harmonic, and so on and so forth now. So, that is the harmonic order now. So, you see that when you have certain voltage of amplitude Vn upon N omega Ls by R, this part is the fundamental reactance, and multiplied by N is the harmonic reactance. The harmonic reactance is proportional to the harmonic order, and therefore, the nth harmonic component current is simply proportional to Vn by N, and that was the reason why we consider Vn by N. So, this Vn by N itself is a measure of a harmonic particular current now, right. So, now let us say this is a single harmonic current. Now, what you need is, you want the RMS value, what you would call as ITHD. So, let us say that you would go into ITHD, and what is this ITHD? You have sigma of In squared, that is, you have the harmonic currents, you may have different harmonic orders, you make a sum of all of them and under a square root, that is the RMS current triple, and this RMS current triple you can divide it by the fundamental current, and this is going to give you the what is called as the total harmonic distortion factor here. So, let me make a few points. This I1 is the fundamental current, and this varies with the load on the motor. It is quite usual to measure this under the no load condition. Why? Because under the no load condition is when I1 is very small. As with load, I1 generally increases and the distortion factor improves. So, normally the worst case scenario is given by the no load, the no load condition of the motor corresponds to the worst case scenario, and we would normally make the measurement under the no load circumstances now. So, now let us see how you get an idea of the weighted THD here, as we can look at here before. So, this In, what you have is, In is simply proportional to Vn by N. So, In is proportional to Vn by N. So, you just do a square of Vn by N and you do a sigma of that, and the whole thing you take under root. This you can see is proportional to the numerator part here, that is, and this you can divide by the fundamental voltage now. So, this is what is called as your weighted THD of the voltage waveform. This is the weighted THD of the voltage waveform. So, why do we call it as weighted THD? Every harmonic component Vn is being divided by N. So, that is the weightage being given. So, the weightage corresponds to how much harmonic current it would be able to inject, and therefore, this is called weighted total. This is total harmonic distortion factor of the current waveform, and that is equivalent to the weighted THD of the voltage waveform. In fact, if you multiply this factor by something like roughly what is equal to the no load inductance of the machine to the block rotor inductance of the machine, you would be able to get the ITHD from here, right. So, this weighted THD is a measure of the ITHD, and that was the reason I listed it as one of the features from a waveform. So, once you have a spectral component, these components can be directly seen, but this particular component requires a lot more calculation, and that basically gives you what is your weighted THD, or it is a measure of the harmonic distortion factor that you will really have here. So, that is because of this model here. So, one of the things that we had there was the fundamental component, that is the most important thing. So, we have to look at how big is the fundamental component now. So, you can't produce whatever you want to. So, there is certain maximum fundamental voltage, as I mentioned earlier, that is possible now, right. So, the maximum fundamental voltage would correspond to the square wave operation, really speaking, but with all the PWM methods there are some limits. If you do not want to go into over modulation, there is some limit now. So, this is sometimes called DC bus utilization, because for a particular DC bus voltage, how much AC voltage you can generate is a question. So, you call it DC bus utilization, right. So, now you see what is the peak phase fundamental voltage. What I mean by that, there is line side voltage, and the line side voltage has the fundamental as well as harmonic components. I am considering only the harmonic component, and I am considering the phase to neutral voltage, that is there is a load RYB with a neutral N. I am considering the load to neutral voltage Rn, that is what I am considering the fundamental component of Rn, right, and I am considering the peak value of the fundamental component of Vrn, that is the meaning of peak phase fundamental voltage, right. If I use sine triangle PWM, what happens is the peak phase fundamental voltage is 50% of VDC, that is what you get there, right. Then with third harmonic injection, you are able to push it a little higher, that is anywhere between 0.5 VDC to 0.577 VDC, depending on what is the third harmonic component you really had. And if the particular third harmonic component is equal to k is equal to 1 by 6, meaning k is the ratio of the amplitude of the third harmonic to the amplitude of the fundamental. So, if the third harmonic injected is 1/6 of the fundamental, then you get 0.577 VDC. This is the third harmonic injection that you get now. So, this is you get something like a 15% increase over that. So, the same thing can also be achieved by bus clamping PWM, and you can push your DC bus utilization to 0.577 VDC. I mean, you can push your peak phase fundamental voltage to 0.577 VDC. And if you go by conventional space vector PWM also, the maximum peak phase fundamental voltage is 0.577 VDC, and if you look at advanced bus clamping PWM also, it is 0.577 VDC. So, that is what is the kind of the theoretical maximum that you can get. This 0.577 VDC is the maximum value of the peak phase fundamental voltage that you can achieve with a DC bus voltage of VDC without resorting to over modulation, without introducing low frequency components in your output voltages. So, let us take a quick relook at this. This is at k is equal to 1 by 6. I have shown a peak signal of this is a sine signal which is of amplitude 1.15, that is something like 2 upon root 3. And if you have these 3 phase sine waves as shown by the red, yellow, blue signals here, we generate a common mode. This is the third harmonic common mode. When you add the third harmonic common mode, what happens? When this goes beyond the peak of that, the common mode is negative, and therefore the common mode brings it lower than the peak value, and you can see that this is how it is now. And the peak value of the modulating signal, though the peak value of the original sine wave is greater than that of the peak of the carrier, the peak value of the new modulating signal is less or just equal to the peak of the carrier now, and this is what makes you it is something like you are packing a higher amount of fundamental voltage without exceeding this peak voltage now. And you compare this kind of a waveform with the third harmonic, with the triangular carrier, you are going to produce third harmonic injection, and you can go up to 1.15. So, this is I am just trying to show this to but that point that it is to re-emphasize that this is 1.15. And similarly, this if it is k is equal to 1 by 4, you can see that I have taken something lower than that. Here it is something like it is 1.15, 2 by root 3, whereas here the peak I am taking is something like only 1.1. Even with that 1.1, you see that the peak of that is very close to that. If I go to 1.15, you can very easily see that this peak will go above 1. So, with k is equal to 1 by 4, it is certainly lower than 0.577 VDC. So, as I have also mentioned before, whereas with k is equal to 1 by 6, you can go to 0.577 VDC. And if you go to conventional space vector PWM, so the third harmonic component, the triplet frequency component is, so this is the sinusoidal component. So, there are 3 phase sine waves, there is a middle valued wave, you take 50% of the middle valued wave, this is your common mode component, which looks roughly like a triangular wave. This looks like a triangular wave because what you are doing here is there is 50% of the R phase wave, and R phase wave is going through the zero crossing. So, close to the zero crossing a sine wave looks almost like a straight line. So, this also looks like a straight line as I mentioned before, and therefore, you go about adding this kind of a common mode component, and the resulting modulating signal is what you get here. And I have plotted this modulating signal for m is equal to 1.15 or which is very close to 2 by root 3, and you can see that the peak value of the modulating wave is almost equal to plus 1 minus 1. So, this is what you can get 1.15 instead of 1 or 1.1547 to be precise instead of 1. So, you have 15% higher voltage than sine triangle PWM. The same way with 60 degree clamp PWM, when you want to clamp the middle 60 degree duration. So, what you are doing is you are adding a common mode signal as shown by this blue dashed line, and the resultant modulating signal is something like what you have shown here, right. So, I have plotted the same thing for 1.1547, that is 2 by root 3, and you can see that it is like here. So, I want to make the point that you really can't exceed 1.1547 now. So, if you look at it here, you can see that this common mode component in this region is positive. As m goes on increasing, now we have looked at m is equal to 0.8, that is the ratio of the peak of sine to the peak of carrier is 0.8. You go about increasing the ratio here to 0.85, 0.9 etc., this value will come down lower and lower, and if it just touches 1, this value will be 0 here, and when it crosses 1, what happens is this becomes negative, and that is what is illustrated here. In this case, you can see that between 60 to 120 degrees, this is m equals, I am sorry, m is equal to 2 by root 3. So, sine 60 is root 3 by 2 times V peak, right. Therefore, the value here is 1. So, this peak is 2 by root 3, this is 2 by root 3 times sine 60, that is 2 by root 3 multiplied by root 3 by 2, therefore, this is 1. So, this sine waveform, it crosses 1 at 60 degree and again comes below 1 at 120 degree. Between 60 and 120 degree, it is higher than that. So, in this entire region, the waveform is greater than the peak and the corresponding modulating signal is less than this now. So, if you add this kind of a modulating signal, you can see that this waveform is equal to the peak at for 60 degrees exactly. Now, let us say you increase it a little higher, from 1.15 you make it to 1.2. What will happen? Here right now there is only one phase which is higher than 1 at any instant of time. So, in this initial instant, this phase which is the yellow phase goes beyond minus 1. The next 60 degree duration, the red phase goes beyond plus 1, and the next 60 degree duration, the B phase goes beyond minus 1, and the next 60 degree duration, the yellow phase goes beyond plus 1. Now, if you go above 1.1547, let us say you consider something like 1.2, what will happen is you will have a situation where the red phase goes positive and also simultaneously the yellow phase will be negative, and it is beyond this minus 1. So, you have plus 1 and here it is beyond minus 1. So, if you have to bring this within the plus 1, you have to add a negative common mode signal. If you add a negative common mode signal, this fellow is already outside minus 1, and so you may not get that, you will this will go beyond minus 1. That is, one of the constraints is by adding this common mode signal, you must produce some MR star, MY star and MB star which are within plus 1 and minus 1, which correspond to the positive and the negative peak of that. That will not be possible if you exceed m is equal to 2 by root 3. I am showing this just with the illustration of 60 degree clamp PWM, and that is true for many of them. So, this m is equal to 2 by root 3 is the absolute limit up to which you can maintain this linearity. I mean, you can produce PWM waveforms without getting into over modulation. If you go into m is equal to 1.2 or 1.3, what is going to happen is you will have a distorted waveform. The MR star, MY star would go outside plus 1 or minus 1. That basically means that there is clamping, and you will see that the resulting is not only the third harmonic component, you will also get other components injected into that. We will discuss this subject in one of our last modules, later modules, which we would call as over modulation, and discuss this problem. When you do not want to go into over modulation, m is equal to 2 by root 3 is the limit, which I would like to re-emphasize. It is not only for 60 degree clamp, it is true for other kinds of PWM methods also. So, I would just stop at that and look at the same thing from the space vector point of view. So, if you are looking at the space vector point of view, instead of 3 phase sine waves, you are going to have a rotating vector which we call as Vref, and in this case it falls within the so called sector 1, and so we will use this vector 1 and vector 2 on the null vector to synthesize this vector over a subcycle, like what we have said this. We will apply the vector 1 for some duration t1 seconds, vector 2 for some durations t2 seconds, such that Vdc times t1 by ts and Vdc times t2 by ts simply add up to the required Vref, and t1 plus t2 is less than the total subcycle time, and the remaining time for that is ts minus t1 minus t2 for that time we will apply the null vector which is here, right. So, this is what we do, and this is how the calculations are exactly done. Vref_Ts, that is the volt second, is equal to this side is the applied volt second. So, V1 T1 plus V2 T2 plus Vz Tz, and the calculations are done like this as I showed in previous classes now. So, you do all this and you look at the switching sequence, the calculations are, here you calculate T1, T2 and Tz, and in conventional space vector PWM you use both the 0 states. So, you apply this for Tz by 2 seconds, then go here T1 seconds, go here T2 seconds and go here for Tz by 2 seconds, and then you come back. So, this is what you do in conventional. In case of clamping, what you can do is you can skip one of the 0 state, for example plus plus plus, you start from minus minus minus, apply this for Tz seconds, apply this for T1, apply this for T2 and back. So, this is clamping, one kind of clamping where you see that the B phase does not switch at all, and the B phase is always clamped to the negative bus. Here it is minus minus minus, it is negative, here plus minus minus, B phase is negative, here plus plus minus is also B phase is negative. So, if you do like this, B phase is clamped to the negative bus. Now, alternatively if you skip minus minus minus, and so you can use this plus 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 can be applied for Tz seconds, this for T2 seconds and this for T1 seconds. If you do that, you can see B and Y are switching, but R phase is not switching now. In this case, you can see R phase is positive here and also positive here. So, in this case I am sorry, the R phase is always clamped to the positive bus. So, you have a situation of B phase getting clamped to the negative bus or R phase clamping to the positive bus whenever your reference vector is in sector 1. So, there are two different kinds of clamping now. So, you can use the sequence 0 1 2 or 7 to 1 to realize your vector in the sector 1. So, there are only two options, either use 7 to 1 in some initial portion, the 60 degree we can't use the same 0 state, we have to change it once in every 60 degrees as I mentioned during my previous lectures on the bus clamping. So, for certain gamma we can apply 7 to 1 and after that we can apply 0 1 2. On the other hand, we can also do 0 1 2 up to this certain gamma and then apply 7 to 1, and this gamma itself can vary anywhere between 0 and 120 0 and 60 degrees now. So, in this case if you are looking at 7 to 1, as I mentioned before, R is clamped to the positive bus here and here also R is clamped to the negative bus. Again, if you do an analysis here, you will find that R is clamped to the negative bus here and here also R is clamped to the negative bus. So, this corresponds to a situation where you have the R phase clamped continuously for 60 degree durations. That is, this is continuously clamped for a 60 degree duration, and if gamma is equal to 30, the 60 degree duration is positioned at the middle of the positive half carrier cycle of the positive fundamental cycle. Otherwise, with change in gamma, the 60 degree position kind of changes, goes to the left or to the right, and the same way it is with R minus like this. So, you have this now. Instead, if you go to the split clamp PWM, as I mentioned before, you have the situation where R phase is clamped to the positive bus here and R phase is clamped to the positive bus in this case. So, these are the durations now. You can see the durations are unequal, and this duration is gamma and this duration is 60 minus gamma, they add up to 60 degree. So, this 60 degree continual clamp is split into two parts, one of gamma and the other one equal to 60 minus gamma, and that is what is split clamp PWM. So, the bus clamping can be classified into continual clamp and split clamp PWM. This is very easy when you look at it from the space vector point of view, right. So, you can say that it's either 0 1 2. If you are in sector 1, you use either 0 1 2 or 7 to 1. Let us say you use 7 to 1 in the first portion of sector 1 and go to 0 1 2. So, that leads to continual clamping. The other alternative, you use 0 1 2 first and then 7 to 1 next, and that leads to split clamping PWM. So, bus clamping PWM, if you look at it this way, it is very easy to just split it into a continual clamp and split clamp, and a special case of split clamp is 30 degree clamp and a special case of continual clamp is 60 degree clamp, right. So, this is the double switching sequence I said, which cannot be done actually using the triangle comparison approach. Why? Because in triangle comparison approach, you are comparing the 3-phase sinusoidal signals, which are samples of 3-phase sinusoids with only one rising carrier or falling carrier. There is only one intersection and only one switching. Here you find R phase switches once and Y phase switches twice. That is not possible with that. It is similar to the bus clamping PWM in the sense that one is not switching. For example, B phase is not switching, and you can see that B is always negative, is negative here, is negative here, is negative here. So, in the entire subcycle B phase is negative. So, this is similar to the bus clamping, but you see that Y phase double switches, and that is why you call it double switching clamping sequence. This is one variety of double switching clamping sequence as I mentioned in previous classes now, and this is another variety of double switching clamping sequence, which is 7 2 1 2, and so you can do this. You start from 7 2 1 and 2. Now, you go about doing this now. We are now, while taking a quick review of this, we are now basically focused on finding out what is going to be the DC bus utilization. So, going to bus clamping to advanced bus clamping, what you can do is in the so called continual clamp you can replace the 7212 by 721 by 7212 or 012 by 0121, and this gives you advanced bus clamping or 60 degree clamp PWM. So, if you generalize that becomes 30 degrees. So, this is again instead of 012 in the bus clamping you use 0121 and 72 instead of 7212 instead of 721. So, this is my advanced continual clamp. So, instead of 721 I am using 7212 and instead of 012 I am using 0121. So, I have advanced continual clamp and we also have advanced split clamp. So, we can use 0121 in the first portion of sector 1 and 7212 in the second portion of sector 2. So, let us just look at how the R phase would be. The R phase is clamped here to R plus, here also it is R plus. This is for a duration gamma and this is for a duration 60 minus gamma. So, the same way you will find R phase is clamped in these portions also, but to the negative phase you will find them clamped in these regions also. This will be R clamped to the negative bus. So, this is advanced split clamp, it is similar to split clamp, but the difference is one of the phases always switches at twice the nominal frequency, right, and this is continual clamp, because here you will see that R phase is clamped to the positive bus continually for 60 degrees, and here you will see that R phase is clamped to the negative bus continually for 60 degrees now. So, you can extend the ideas of continual clamp to advanced continual clamp by using these sequences 7212 and 0121. Similarly, you can extend the idea of split clamp to advanced split clamp by utilizing the sequences 0121 and 7212. So, this is what we have been doing now. In all these cases, we are we are handling the problem in the space vector domain. So, in the space vector domain you have the 6 vectors like this, and this is active vector 1, 2, 3, 4, 5, 6, and you can join them using a hexagon now. So, you have this V reference vector, and the V reference vector should have the same magnitude in subcycle after subcycle over the entire cycle. So, if that is the case, the highest value it can take is equal to the radius of the inscribed circle. This corresponds to the highest value of reference vector magnitude, and that is Vref is equal to 0.866 VDC. That is, the side of this hexagon is VDC and each cos 30 degrees. The 0.866 VDC is the highest value of Vref. Now, when Vref is 0.866, let us say Vref itself is rotating. Let us consider a particular instant where Vrn is at its peak. That is, when Vrn is at its peak, the reference vector will be here, will be aligned here like this, will be like this. So, let me draw that here for your benefit. So, okay. So, at that instant it will be like here. This is where your V reference vector will be when Vrn is at its peak now. And under this instance you can see that your V alpha is 0.866 VDC, and what is your V beta is equal to 0. So, you can use the space vector transformation. V alpha is equal to 3 by 2 times Vrn, and therefore, Vrn peak is simply equal to 2 by 3 times 0.866 VDC, and what is 2 by 3 times 0.866? That is 0.577 VDC. So, this is a proof from the space vector point of view why peak phase fundamental voltage is equal to 0.577 VDC. I mentioned this very quickly in one of the previous lectures. Here I have taken the time to just go through some more steps. So, you can look at it either from the triangle comparison point of view or space vector point of view. You will find that conventional space vector PWM, third harmonic injection with 1/3 and bus clamping PWM all would give you a maximum value of 0.577 VDC for the peak phase fundamental voltage, and any space vector based PWM would give you something like 0.577 VDC. So, this is what you get now. So, when you go to something like advanced bus clamping PWM, you have the advantage of space vector PWM, of conventional space vector PWM, namely of this increased AC voltage. In addition to that, there are certain advantages in some under certain operating conditions, like in terms of line current ripple, as we would see probably in a little while, or and also in the next lecture now. So, you have this now. So, we had looked at the harmonic spectrum of sine triangle PWM earlier. If you look at the harmonic spectrum, for example, of the bus clamping PWM, the structure is kind of going to be very similar. So, you have the output voltage, we are considering the output voltage Vrn, okay. That is, R is the load terminal, N is the load neutral. We are considering that voltage, and if you look at the components, as before, you will have the fundamental frequency component F1. I am sorry, this is the fundamental frequency component F1 now, and you will have a large break, and there is carrier frequency Fc, there is 2Fc, there is 3Fc, there is 4Fc, and around this you will have harmonic components as before. You will have harmonic components as before. So, this is the nature of the harmonic spectrum for bus clamping PWM in general, and you see from PWM method to PWM method this will change. With sine triangle PWM you will get something, and if you add third harmonic injection the harmonic components will change. Let us say in bus clamping PWM, if you look at 60° clamp PWM and if you look at 30° clamp PWM for the same fundamental amplitude, you will find that there are some small differences in these harmonic amplitudes, and that is what causes certain difference in the line current ripple. We will not go into what would be the amplitude with 60° clamp and what would be the amplitude in 30° clamp, rather we would try and understand how the RMS line current ripple will be different in these two methods in our methods of analysis. So, now right now this is what I will say, that this is Fc, 2Fc and 3Fc. You have the first harmonic sideband and the second harmonic sideband, third harmonic sideband and the fourth harmonic sideband, right. When you looked at the similar thing for carrier in the sine triangle PWM, your Fc itself was equal to the switching frequency. Now, in this case this is equal to 2/3 of switching frequency. This is equal to 2/3 of I am sorry, it is 3/2 times the switching frequency. That is, if you switch at Fc, right, this is the carrier frequency, it is always not switching. That is, what is my switching frequency? My switching frequency FSW is 2/3 times the carrier frequency, or carrier frequency is equal to 3/2 times FSW. So, what you have is, this is Fc or 3/2 times switching frequency. So, what you can do is, when you go for a third harmonic, when you go for bus clamping PWM, what happens is your effective switching frequency reduces to 2/3 of the carrier frequency. That can give you some benefit in terms of reducing the switching loss, but your harmonic amplitudes can increase, actually speaking. On the other hand, what you can also do is, you can maintain the same switching frequency. How can you maintain the same switching frequency? By increasing the carrier frequency by 1.5 times. You can increase the carrier frequency by 1.5 times to maintain the same switching frequency as sine triangle PWM or conventional space vector PWM. If you do that, what happens? This whole thing gets shifted by 1.5 times. So, when the whole thing gets shifted to the right by 1.5 times, what happens is, the harmonic reactances seen by these components are increased. So, one advantage with bus clamping PWM, as I mentioned before, is reduction in the switching frequency. You can make use of that advantage, and that would reduce your switching loss and the heating in the inverter. On the other hand, what you can also do is, you can maintain the switching frequency same as in the sine triangle PWM, and therefore, you can increase the carrier frequency by 1.5 times. If you are increasing the carrier frequency by 1.5 times, let us say we are considering 5 kilohertz switching frequency, this becomes 7.5 kilohertz instead of 5, this becomes 15 kilohertz instead of 10. So, the sidebands get shifted by 1.5 times, and the reactance seen by them increases by 1.5 times, and that is going to reduce the harmonic currents driven by these components now. Therefore, these bus clamping PWM methods have an advantage in terms of line current ripple, particularly at high modulation indices. At high modulation indices, when we have the same switching frequency, when we increase the carrier frequency by 1.5 times. So, that is something that I would like to mention here now. The same way, if you look at the advanced bus clamping PWM, the basic structure would look similar. The basic structure would look similar. So, you have the amplitude versus frequency, you will have the fundamental component, and there is a large separation. So, here we can't talk of carrier frequency, we would talk in terms of the switching frequency. This is the average switching frequency. What is average switching frequency? It is the switching frequency averaged over a line cycle. Sometimes a phase switches at nominal frequency, sometimes at double the nominal frequency, and sometimes it is clamped, and the switching frequency is the average value of the switching frequency over a line cycle. You have FSW, you have 2 FSW, you have 3 FSW, and so on, and 4 FSW, and so on, and you will once again have harmonic components around these. You will have harmonic components around these. This is how the nature is going to be. So, all these methods will actually differ, for a same fundamental voltage you will find that their harmonic components are different. So, we have to just understand that how different they are. Sometimes they may be different for better, sometimes they may be different for worse. So, for certain modulation indices, for some magnitude of the fundamental voltage, let us say conventional space vector PWM will be better than some other PWM, sometimes vice versa. If you take a high modulation index, what you will find is advanced base clamping PWM will be better. I will tell you how. So, what happens is, now I have shown a case where the first sideband is a little more than the second sideband now. So, what happens in the case of at very high modulation indices is the second sideband becomes dominant than the first sideband. So, let me just draw something in a different color. So, for example, you may have the second sideband like this, but the first sideband may be like this. So, the second sideband is dominant. When the second sideband is dominant, the second sideband sees much lower current. It sees it sees a double the leakage reactance, and therefore, the corresponding current is low. This happens at high modulation index. So, at high modulation indices, the advanced bus clamping PWM results in lower one than conventional PWM. If you look at the conventional case, I will show you in a different color, let us say green color. In conventional, what you will find is, you will find the dominant component something like this, and the second the sideband component something like this, as I have indicated. See, these are all indicative, just to get some feel for the problem. So, in conventional, you have the first component at some high values of modulation index, you get the first component is dominant and the second component is not so dominant. So, the corresponding current, this dominates, the leakage reactance seen by this component is not very high, therefore, there is some RMS current ripple. Whereas, in the advanced bus clamping PWM, the second sideband is dominant and second sideband is double the leakage reactance than the first sideband harmonic. Therefore, the current ripple produced by this is lower. Therefore, advanced bus clamping PWM, you will find these advantages usually at very high modulation indices, and so this has been given in some reference. So, this particular reference particularly, this is mentioned in this advanced bus clamping PWM techniques paper. This has been indicated now in this paper, this Tushar, Bhavsar and Narayanan. There has been a more exhaustive comparison of conventional space vector PWM and the advanced bus clamping PWM methods. The dominant component of the first sideband and the dominant component of the second sideband have been compared over the range of modulation indices, and so for a detailed quantitative study of this, you can really look at this paper and get an idea of how the different PWM methods are different, how their spectral components vary with modulation index now. So, with this I end this lecture. So, we have been trying to basically look at this PWM methods and we had a relook at the PWM methods triangle comparison, the space vector ones, and we tried to see how much is the DC bus utilization, and we have been trying to look at the harmonic spectrum now. In the harmonic spectrum, we have the fundamental component and we have the switching frequency components now. For the same fundamental component, different harmonics will give you slightly different switching frequency components, and that is what is the difference in terms of waveform quality between the various PWM methods. And what you would normally find is conventional space vector PWM is good at low modulation indices and even at medium modulation indices. At high modulation indices, you will find that the discontinuous PWM method or bus clamping PWM method will slightly improve, and at very high modulation indices close to full modulation index, advanced bus clamping PWM method is what is very advantageous, and that you can look at the reference I indicated to you. And I thank you for your interest in this and look forward to seeing you again in the next lecture. Thank you very much.